Welcome and hello. This is a video exercise using the FHWA hydraulic toolbox. I'm titling this exercise Watershed Time of Concentration. So what we're going to be solving for is the time of concentration in a watershed. And we're going to be using the rational method calculator as well as the Weir calculator. So what you see on the screen here is the problem statement. First, we're finding the time of concentration. And then below that, we've been given some watershed data and some Weir data. So the idea here is during a 10-year storm event over Nashville, Tennessee, that flow rate is going to run through this weir. And we have two different values for H on the weir. That's the height through this rectangular weir with a given base width of 12 feet. So we also have some watershed parameters. Like I said, return period is 10 years, runoff coefficient, the total area, and ultimately we're going to be solving for this time of concentration for two different times of concentration, actually one for each different height of flow through the weir. All right, so here is our hydraulic toolbox. To solve this problem, we're going to utilize two different calculators. So with our project selected, click on calculators, and the first one is going to be new Weir analysis, the Weir calculator, as well as the rational method calculator. To get started, actually go ahead and make sure you have US customary units selected if you're following along. And then what we're going to use is the rational method to solve for the time of concentration T sub C, which is a function of the intensity. And the intensity can be back calculated using the rational method Q equals CIA times the constant. Because we know the area, we know the flow rate using the Weir data, we'll determine that. And then we also have the runoff coefficient of 0.45. All right, so what I'm going to do first is determine that flow rate for the two different values of H in the Weir calculator, and then we'll move over to the rational method calculator and determine that T sub C's for the two different heights. All right, so back to our toolbox, and now I'm going to right-click on the Weir analysis, Weir data, and then let's start putting in our Weir data here. The Weir type is rectangular, so that's already selected and good to go. The weir length, this is the width across the weir that was given as 12 feet. The weir coefficient was also given as 3.2. And then over here on the right side, we need to enter the head or the flow. And we're going to enter the head because that's what we were provided. The flow is what will be calculated. So I'll just type in 2 feet and 3 feet. Let's go with 2 feet first. Click on calculate. And then the resulting flow rate is 108.6 CFS. So I'm going to write that down in my notes for the 2-foot head through the rectangular weir. And then the other head value we need to determine the flow rate for is 3 feet. So I'll type in 3, click on calculate. 199.5 CFS is that flow. So I'll go ahead and write that down in my notes as well. Okay, so with those two different flow rates, we have the Q variable now in our rational method. Let's head over to the rational method analysis. This is where we're going to be typing in our runoff coefficient, our area, and we also know the two different flow rates, but we need to determine that rainfall intensity to determine the time of concentration. Let's start off with the runoff coefficient here. This is one thing we do know for sure, 0.45. We were also given the area in acres is 100 acres. All right, so far so good. Next up is the rainfall intensity, and that's going to ultimately calculate the flow rate. And associated with that is the time of concentration, which is ultimately what we're looking for. But it's sort of something we have to solve all at once. So let's click on the compute button right here. And then for our IDF curve computation method, I'm going to select this first option, Hydro 35 data used in eastern and central United States, and then click on the button to define storm data. So what we have in this dialog box is the depth of precipitation at our specific location for 2-year and 10-year return events, and storm durations being 5 minutes, 15 minutes, and 60 minutes. The units here are in inches. So I'm going to bring up a PDF document, which is what we're going to be using here to determine those 6 different precipitation depths. This is called the NOAA Technical Memorandum NWS Hydro-35. It contains 5-minute to 60-minute precipitation frequencies for eastern and central United States, just what it says. I'll leave a link to download this PDF file in the description of the video. Basically, if we scroll down a couple pages, we get to the table of contents, and we see that for figures 4, 5, 6, 7, 8, and 9, we have those 6 different return periods and storm duration maps. They are going to provide us the precipitation depths over the central and eastern parts of the United States. So let's just do the first one as an example. 2-year, 60-minute precipitation. It says it's on page 15. In my PDF file, it's actually page 20. So here it is. I'm going to scroll down a little bit, zoom in, and confirm indeed this is the 2-year, 5-minute precipitation map. And what we have are lines on this map with county outlines and state outlines as well. It's a little bit blurry and kind of hard to read, I'll give you that. But what we're looking for is to ultimately find our location and then interpolate between the lines that represent the precipitation for this 2-year and 5-minute storm event. So here is the outline of Tennessee. Again, sorry if it's hard to see. Nashville, I'd say, is probably right about here where the hand is. So this is 0.475. Right here is 0.45. That's in inches. Let's just call it 0.44. So pretty much on the line there. I'm going to go back to my calculator, change this to 0.44 inches, and we're done with that 1 of 6 precipitation depths. Okay, next is 2-year, 15-minute. I have written down in my notes, this is a couple pages down. So, yep, here it is. 2-year, 15-minute precipitation. Okay, so I'm going to find my location of interest once again. It's right about here. 0.90 inches of precipitation is right here. This line right here is 1.0, so then further north would be a little bit less, like 0.8, but it's really close to 0.9. So I'm just going to estimate 0.89, and that's inches for the 2-year, 15-minute storm event, 0.89 inches. Okay, so I'm going to continue that process with the remaining 4 precipitation depths that are required. I did that off camera, so I'm just going to type them in here live, 1.55. And then we have 0.81, 1.70, and 3.50 inches. All right, so when I click OK, what we have is our data right here. So let me make that a little bit wider. Everything from 2-year to the 100-year return events, recurrence intervals for those storm durations. We have everything from 2-year data up to 100 data because an interpolation process took place to generate some numbers for 5-year, 10-year, 25-year, and 50-year. So all the data on these different rows were just generated automatically, and that is only for the 5-minute, 15-minute, and 60-minute. So the 10-minute and the 30-minute data was also interpolated for the 2 return periods that we actually saw maps for, which was 2-year and 100-year. Anyway, we typed in precipitation depths. The numbers that we're seeing here is precipitation intensity, so in units of inches per hour, which is why the actual numbers don't match up except for the 1 hour. So we actually did type in 1.55 and 3.50. Okay, anyway, this data right here is used to generate the curves, the intensity, duration, frequency curves, as well as generate this, what is, I assume, a line of best fit to describe that curvature. All right, so what we're interested in the problem statement said the 10-year storm event. So based on the row of this table that I select, the IDF equation for the intensity based on the time of concentration changes. You can see how it's taking on the same form, but the actual numbers are a little bit different. So I'm going to stick with 10-year as my return period. Over on the left-hand side, I need to specify a time of concentration. So I'll click on specified T sub C. And then once I type a number in here, click on compute intensity. It will update the intensity with the calculation here. And then that will be used to generate the flow rate. Now, we already know what the flow rate is. That is 108.6 CFS and 199.5 CFS. We also know we're dealing with the 10-year return period. But what we don't know is the T sub C or the intensity. So we're going to use this calculator and just sort of figure it out. I propose what we do is we start with a larger than necessary time of concentration, which will put us further to the right on this plot right here. The intensity will be lower than it probably really is. and that would result in a flow rate that's lower than it probably is. So as we decrease the time of concentration, the intensity will be increasing, the flow rate will be increasing. Eventually, we're going to hit our flow rate of 108.6 CFS, and at that particular flow rate, the time of concentration will be our answer for the problem. And then we'll continue decreasing the time of concentration until we get to the second flow rate of interest, which is 199.5 CFS. Okay, so I'm just going to randomly throw out a flow rate or a time of concentration here. I'll say, how about 3 hours? That's probably too large, but that's also the point. So I'll tab off and then I'll click on compute intensity. It's giving me 1.168 inches per hour. So what I'm going to do is click on done. 1.168, or I guess 1.17 has been copied over here to the rational method calculator. And sure enough, the flow rate has calculated. It's 53.0 CFS. So that's a little bit too low, and that's fine. What we're looking for is 108.6. So I'm going to go back to the dialog box here, and I'm going to change the time of concentration to something less. So instead of 3 hours, let's go with 2 hours. I'll click on tab, click on compute intensity. It increased up to 1.524 inches per hour. So I'll click on done. Now we're up to a flow rate of 69.1 CFS. Still quite a bit off our target of 108.6. So let's repeat that process once again. Sticking with round numbers, let's just go for 1 hour now on our time of concentration. Tab off, compute intensity, 2.351 inches per hour. I assume that's going to be a lot closer, so I'll click on done. Our flow rate is a lot closer. It's 106.7. Again, we're looking for 108.6. So this is really close, probably just a few minutes off because we're just a couple CFS off of our target for our first value, H equals 2. So let's go with how about 58 minutes? See what happens there. Compute intensity. The intensity is 2.40 inches per hour exactly. Click on done, and now we have a flow rate of 108.9 CFS. So we were looking for 108.6 CFS. So I propose that that is a satisfactorily correct answer. In fact, as far as precision is concerned, I don't think changing this to 57 or 59 is going to be any closer. I think 58 is the time of concentration, and it's going to be the closest to the nearest minute. Let's just stick with the integer minute precision for our time of concentration. All right, so we got one of our time of concentration solved for. We're almost there. Let's go ahead and just continue to decrease that time of concentration, searching for now a flow rate of 199.5 CFS. So instead of 58 minutes, let's just go 30 minutes. Maybe a little bit too low, but we'll see what happens. Compute intensity, that returns a 3.484 inches per hour. Click done. 3.48, that results in a flow rate of 158.1 CFS. Okay, so not quite there. We're looking for 199. So click on compute. Let's go ahead and change this now to 20 minutes. That returns a intensity of 4.268 inches per hour. Click on done. Now we're up to 193.7 CFS. So again, just about 6 CFS off, about 3% difference. So let's see, since the rational method is linear in nature and 3% of 20 is 0.6, if we subtract 0.6, it'd be 19.4. We'll just see what 19 does and then tab off. So time of concentration, 19, compute intensity, 4.327 inches per hour. We'll click on done. And that gives us a flow rate of 198.4 CFS. Okay, so I conclude that that is the closest that we're going to get. If I change it to 18, let me just change it to 18 out of curiosity. Compute intensity, done. 203.3. Yeah, we were closer with 19 minutes. Can I change this right here? Can I just go 19 and then tab off? Oh my gosh, yes, I can. Okay, so I guess I didn't have to continue visiting this dialog box the way I was doing that. That's what I want to do, 19. And okay, that's already saved, done. And 198.4. Okay, we're about 1.1 CFS off, but again, this is the closest time of concentration to the nearest integer minute. Well, that's it for this exercise. What we did was we determined the time of concentration for a specific watershed with a specific runoff coefficient at a known location for two different flow rates, which we determined using the weir calculator, and the dimensions and height of water in that weir.